Humanity has discovered these stunning mathematical equations that describe atoms, stars, black holes, even the rapid expansion of the universe itself. But it leaves us with this really profound question. Do we actually understand all the laws that govern reality? Welcome to The Explainer. Today, we're exploring whether physics can ever reach a complete, unified mathematical description of nature, or if the cosmos is, always going to keep its best secrets hidden.
Okay, let's dive into this. To make sense of these dizzying cosmic mysteries, we'll break it down. We're going to start with the four fundamental forces and the standard model, move out to gravity and space-time, and then tackle the great unification problem. Finally, we'll venture into the dark universe and look at why this whole thing remains an unfinished revolution. Before we ask if we have all the laws, we kind of have to recognize what a physical law actually represents. In physics, these aren't just, abstract ideas. They're rigorous mathematical equations discovered and tested by scientists that dictate exactly how nature behaves under specific conditions. Mathematics is literally the fundamental code of the universe. So the question is, do we have the full source code, or are we just looking at a few isolated lines? Section 1. The four fundamental forces. Because, to figure out what we don't know, we have to start with a baseline of what we do know. For centuries, scientists have been trying to describe the interactions that shape our universe. Today, we know there are four fundamental forces. First up, gravity. Now, despite being the absolute weakest force, it works across infinite distances to shape galaxies and the whole cosmos. Second, electromagnetism. This carries light, keeps electrons in orbit, and powers literally all our modern tech. Third, the strong nuclear force, the absolute strongest of them all, which binds the nuclei of atoms together. And finally, the weak nuclear force, which operates on these tiny subatomic scales and is responsible for certain types of radioactive decay. Section 2. The standard model. So how do all these forces actually interact with the matter that makes up you, me, and the stars? Let's move from the macro down to the quantum micro. The standard model of particle physics organizes our reality beautifully. It maps out the fundamental building blocks, particles like quarks and leptons, and shows how they interact through force-carrying bosons, along with the Higgs boson giving them mass. It perfectly integrates electromagnetism, the strong force, and the weak force. But if you look closely here, notice a glaring plot twist. Gravity is completely missing. No way around it, the standard model simply ignores it. Section 3. Gravity and space-time. To find that missing puzzle piece, gravity, we have to zoom all the way back out to the macro universe. While the quantum world has the standard model, the macroscopic world relies on Einstein's general relativity. Einstein totally revolutionized physics by describing gravity not just as some invisible tether, but as the actual curvature of space-time itself. Imagine it like a bowling ball on a trampoline. Massive objects warp the fabric of space, and that curve dictates how planets, stars, and even light move. And this theory has been extraordinarily successful. It perfectly describes black holes, the orbits of planets, and those massive gravitational waves rippling through the cosmos. Section 4. The Great Unification Problem. So we've got two spectacularly successful theories, the standard model for the tiny stuff and general relativity for the massive stuff. The problem? They absolutely refuse to work together. The crucial point here is that these two frameworks describe reality in fundamentally incompatible ways. General relativity sees the universe as smooth, continuous, and predictable, like this beautifully curved geometric landscape. Quantum mechanics, on the other hand, it sees a discrete, jumpy, and highly probabilistic world built of particles and fields. Things behave very, very differently down there than in our everyday experience. When you try to use the math of general relativity to explain extreme quantum spaces, like, say, the deep interior of a black hole, or the very moment of the Big Bang, the equations literally break down. They give impossible answers. It's almost like the universe is practically mocking us. And that brings us to physics' biggest headache, and honestly, its holy grail, quantum gravity. Physicists at places like the Perimeter Institute are desperately investigating ways to merge these domains into a single set of principles. They're exploring mathematically intense ideas like string theory and loop quantum gravity, but it's vital to maintain some epistemic humility here. Despite decades of brilliant work, no universally accepted final theory of quantum gravity has been established yet. The revolution is very much incomplete. Section 5. Exploring the dark universe. Because, as if unifying quantum mechanics and gravity wasn't hard enough, the late 20th century revealed a much deeper mystery.
The true scale of what we don't know is actually kind of staggering. Everything humanity has ever seen, touched, or observed, every star, planet, galaxy, and atom described by the Standard Model, makes up just 5% of the cosmos. Just 5%! The rest is entirely invisible to us. Roughly 27% is dark matter, and a massive 68% is dark energy. They dictate the structure and fate of the universe, and we honestly don't fully understand what either of them actually are.
Let's start with dark matter. Scientists have overwhelming observational evidence that galaxies contain way more mass than we can see. There's this invisible gravitational glue holding them together. But what is it? Current scientific candidates include WIMPs, weakly interacting massive particles that would pass seamlessly through normal matter. There are also axions, which are hypothetical low-mass particles. Some even suggest primordial black holes formed right after the birth of the universe. Scientists are hunting for these right now, but none have been definitively proven yet.
Then there's dark energy, which is doing the exact opposite of holding things together. It's this mysterious force causing the universe's expansion to accelerate. Hypotheses for this one range from vacuum energy to cosmic space wrinkles, or maybe even a flaw in general relativity itself. But dark energy and dark matter aren't our only headaches. We still can't explain why there's more matter than antimatter, why fundamental particles have their specific, seemingly random masses, or why the universe has the highly specific laws and constants that it does. The mystery goes incredibly deep. Section 6. An unfinished scientific revolution. With all these missing pieces, quantum gravity, dark matter, dark energy, fine-tuned constants, where does this actually leave our quest to understand everything? Physicists dream of finding a theory of everything. Ideally, this would be a single, unified mathematical description connecting quantum physics, gravity, matter, forces, and cosmology. But even if we do find the foundational equations of reality, humanity faces some hard limits. We're bound by the limits of our observational tools, the immense energy scales required to actually test these ideas, and cosmic horizons we simply cannot see past. So a theory of everything wouldn't mean we could predict every single event in the universe. It would just mean we finally understand the foundational rules of the game.
And remember, science is an endlessly evolving process of approximation. Even Einstein struggled with the unknown. When he originally formulated general relativity, he added a cosmological constant to keep the universe static. Later, when he learned the universe was actually expanding, he removed it, supposedly calling it his biggest blunder. But ironically, today that very mathematical constant is one of our best ways to explain the vacuum energy of dark energy. It humanizes science perfectly, right? Our current frameworks are wildly successful, but they're likely just approximations of a much deeper, undiscovered law.
Which leaves us with this final thought. We've decoded the DNA of stars and mapped the echoes of the Big Bang. But 95% of the universe remains in the dark, and the quantum world still refuses to speak to gravity. Will humanity ever unveil the ultimate final laws of reality? Or is science an endlessly beautiful, unfinished revolution, where every answered question simply reveals a vast, new horizon of the unknown? Thanks for exploring this explainer with us today. Keep looking up and keep questioning everything.